Good afternoon. Here we are. My name is Carl Rundy. This is the Physics 203 video lecture. Physics 203 Fall 2020 video lecture 1. Good. So let's just get started. Here, I'll put my name here. Let's get started with the syllabus I sent out. It's about as short as you can make one of these things. And I'll just go through it. The office hours will be by email for now. Until further notice, all we're doing is YouTube channel, YouTube videos, and email office hours, and then we'll build up from there. Okay, so what do we have? Office hours at my email. I'm going to write this down here. It's in front of you on the syllabus. csufresno.edu. And the next point I'm going to make, I'm going to skip down to the homework here, because the big deal this semester is that I'm asking that people send in pictures of their handwritten notes once a week. I did this with some of my lower division classes last semester. It worked so well. It's really one of the main things I can offer you. Help keep on track. So at the end of the week, Friday 6 o'clock, no later than, you have taken pictures of the entire week's worth of lecture notes and send them in. And send them to my email account. And always, when you send them in, start a new message. So it's not attached to some other message. Start a new message, and then I have that right here. Yeah, for the subject, it will be your name, and then Physics 203. Yeah, Physics 203. And then everything, homework and things like that, can come in here. If you're sending homework in, actual homework sets, then you want to make sure you have an app that converts those homework sets to PDF files. If you're just sending pictures of your notes, it works pretty well to lay them out and take pictures of them. But anything I actually have to print out, then you're going to want to have a conversion to a PDF file. There are free apps for these cameras, so there's no problem there. Okay, so that's the big feature of this semester, those lecture notes, handwritten once a week, and you can make them as nice as you want. I recommend spacing, leaving a lot of space in them. You can come back, work on them, improve them, and so forth. Good. Everything else, like midterm exam, final exam, which I put down here, and the grade, I forgot to put the grade scale on this. It's just 90, 80, 70, 60. But in reality, at the end of the semester, I see how everybody did. So I can add that and send you an amended syllabus. Nothing to worry about here at the beginning of the semester. Okay, what else? So yeah, my YouTube channel, Carl Rundy, it's going to have a Physics 203 playlist. All of my lectures have their own playlist, and I'll just keep putting the new lectures in there as they appear. It also says homework assignments are announced in the videos. So I've done this recently too. I'm trying to improve it, but I'm going to build the homework problems into the flow of the lecture. Sometimes I even get you started on them, and that way we have to keep track of what was supposed to be a homework problem and when it's due, but we'll manage that as well. Okay, so the lecture notes you can definitely send in as a separate file, and then the actual problem sets you can send in as a separate file, always using this format. The text You know, I could write down a few texts. There is, strictly speaking, no required text, but a very standard one is Goldstein, second or third edition, Classical Mechanics, Landau and Lifshitz. If you don't know any books by Landau and Lifshitz, here's a good time to find them. See if you can get a used copy. Landau and Lifshitz Classical Mechanics, a slim volume. These were some of the great Soviet physicists. Yeah, fantastic. What else do we have there? I had Marion, or Marion and Thornton, is an upper division level book, a very good book. You can definitely refer to that. And there's V.I. Arnold. That's really pretty high level mathematician style of classical mechanics. And of course there are many more books. This is very standard material, but the way we put it together isn't necessarily completely standard. So I hope to give an interesting presentation of the subject to you guys. So that's enough for the formalities. It can be summarized in YouTube lectures, handwritten notes, and email office hours. Okay, good so far. So I'm going to do something of a lecture today with material, but I'll begin with a course outline. Okay, this one goes up, this one comes down. There we go. I'll begin with a course outline. These things are only so good at the beginning of the semester, but let's just start numbering some things. First, I'm going to do a Newtonian point mechanics review, just for formalism. Newtonian point mechanics review, and let's say including conservation laws. And from there, I want to do a derivation of something called the principle of least action. So then next, derive, I'll put that in scare quotes, principle of least action. This is material in chapter 1 of Goldstein. And from here, we get this principle of least action, but we don't really know how to use it. Then we talk about the variational calculus on its own. Variational calculus on its own, that's a mathematical technique that is independent of physics, actually. But it allows us to explore the principle of least action and then go into Lagrangian mechanics. So after variational calculus, all right, Lagrange and applications. So that's a major emphasis at that point. This is moving into it. This is the major emphasis. We're doing Lagrangian applications, for example, small oscillations and things like that. In fact, why don't I just write here small oscillations, and central force, scattering. So you find all these things in Goldstein and their respective chapters. So what I'm going to write here, coming up later in the semester, I'll just mention briefly because there is kind of a whole program that we're unfolding. So then we have to do Hamiltonian mechanics. I'll just write Hamilton. Okay, so Hamiltonian mechanics, Hamilton-Jacobi theory, that's about as far out as you get in classical mechanics. But then I'm going to do an introduction to fluid mechanics. Okay. So introduction to fluid mechanics, and that's a field theory. That's continuum mechanics, basically. So one could do a lot there, but I have a certain goal in mind. Introduction to fluid mechanics. Write that down, because we then get to the small small velocity approximation, the short wavelength approximation. So I'm going to write waves and the Eichenall equation, which you may or may not have heard of, but these would be topics that you could get in electricity and magnetism just as well. The reason I'm bringing them up for our classical mechanics course, by doing fluid mechanics, we actually never leave the basis of mechanics. So we're doing fluids and we do waves, Eichenall equation. And finally, there's a very interesting connection between this branch of physics here and this one right here. So what we end the semester with is Hamilton-Jacobi equation, Eichenall equation, and Schrödinger's equation of quantum mechanics. They all tie together very nicely, and they also really tie together all of the variational calculus aspects. So this is going to be a nice program that we're going to go through by hook or by crook. Okay, so that's an outline, and you can see these various and assorted topics in Goldstein and other books. And we've got nothing but time at this point. We're right at the beginning of the semester. So let me check how we're doing with our nothing but time. Yeah, we're going to finish up with a short lecture just so we have something to turn in on Friday. You don't necessarily have to turn this in, although you can turn in all your notes, but I'll get going with some of this review of Newtonian point mechanics and the conservation laws. Good. Let's have it go. Okay, so what do we have? We have Newton's law of motion. Newton's laws, 1, 2, and 3. We have inertia, law of inertia, and then the one we're going to focus on So this is actually the formalism right here, that you have a differential equation, second order differential equation, mass times acceleration, force as a function of position, velocity, and time, in the most general case. And then for the third law, you have, if you have, say, two, those are tennis balls, okay? You have two objects interacting, and you say the force of one acting on two is equal in magnitude, opposite in direction, the force that 2 exerts on 1. So it's often said that the first law is contained in the second law, and then one can more generally discuss inertial reference frames and things. Okay, so if we want to talk about point mechanics, this is a single point particle, the law of motion for a single point particle. I want to talk about point mechanics of systems of particles. Then you have to have, well, let's go ahead and draw our little cloud of particles here and label them. That's 1, r sub 1, 0.2, r sub 2, etc. Okay. So then we can generalize this law right here to say that m sub I, so mass times acceleration for the individual, it's got subscript there, is equal to F sub I. And it can be very useful to write it as follows. So mass times acceleration, vector, mass times acceleration equals external. So this is an, I'm just writing it there. This is the external force on the ith particle. And then the internal forces, the reciprocal forces of these particles on each other, you could say that's Fij, and you would sum j equals 1 to n, so you've got n particles, I equals 1 to n, j as well, and then j is not equal to I. Okay, so then formally you've got Newton's law for a system of particles. Go ahead and put a box around this. And to come back to this external force, it says basic as, say we have these two particles that are interacting with each other, would be those forces. And the external force would be the force common to them, for example, gravitational force acting on them in this room, causing them to fall. So you could break up the forces into the external force and the forces of interaction between the particles. Good, and of course this still holds for every pair of particles in this set of particles. Third law still holds. Okay, so what we want to do is just remind ourselves of the conservation laws. Conservation laws for this system of particles. Good. There's our set of equations. And conservation laws. So the first thing we're going to look at is the case where the force can be derived as the gradient of a scalar function. So let f sub I be equal to minus the gradient sub I of a function u of R1 to Rn. And my gradient sub I means that I'm going to take the three spatial derivatives that go along with the ith particle. Okay, so gradient sub 1 would be for R sub 1, gradient sub 3, R sub 3, gradient sub n. Those three derivatives for R sub n. Okay. the three partial derivatives that go with x, y, and z sub n. Okay. Yeah, so suppose we have such a function then consider this expression here, 1/2 sum of m sub I r sub I dot squared plus u of r1 to rn. Okay. That looks like the mechanical energy. It's the sum of all the kinetic energies plus this function whose gradient is related to the force, like that. Okay, so what do we do now? We take the time derivative of this function, dE dt, and we have 1/2 sum m sub I. Now this r sub I dot squared, r sub I dot squared is equal to, this is how we're defining it, the scalar product, the dot product between these two vectors. And I could even say it's xi dot squared plus zi dot squared, okay? Because when I take the time derivative of this now, you can see in my chain rule, 2xi dot d dt xi dot squared is 2 second derivative like that. So that's the time derivative, and I have the sum of those three time derivatives, okay? So what I get here is 2 r sub I dot dotted into r sub I second derivative. So leave yourself some space on these kind of calculations if you have to refresh your memory on how these go. There's the part of it. You do it for y and z, and then you'll see that you have 2 times the scalar product between the velocity and the acceleration. Just like you have on your chain rule, 2 times x dot x acceleration. Okay. So that's so far so good. Now, the time derivative here, we have to use the chain rule of multivariable calculus, and that will turn into a sum. We're going to have the gradient, the gradients of I of this u, r1 to rn, dotted into r sub I dot. Again, this one, leave yourself some room, and the example calculation for that is du dx dt. You know, for a single variable case, it's just a chain rule here. Then the chain rule for multivariable calculus tells you to do it for the ith slot and sum over all of them. Okay, so that's what we get right here. So far, so good. Finally, well, you actually want to leave these up here. Let's just erase the top of the board and see if we can squeeze that in. See if we can squeeze the punchline in right here. What we have is we've differentiated this mechanical energy with respect to time. 2's cancel. We're going to have mi ri second derivative. I'm going to factor out this ri dot because I have it here as well. So then I'll have gradients of iu. I'll leave the cleaner here. Okay, leave the dot product ri dot sum I equals 1 to n equals 0. So we have this big sum here is equal to 0. Oh, jump the gun. We don't have the sum is equal to 0. We just have that big sum. Now, what we do have, though, is that this expression here is the same as mi ri second derivative minus f sub I. And that is 0 because that's just Newton's law right here. Okay. Just Newton's law right here. And so we have a sum of zeros, and therefore this thing is equal to 0. And that tells us that this combination that we call mechanical energy is conserved. So it's equivalent to having a potential energy function that does what this one does, is equivalent to having conservation of mechanical energy. Okay, so that's pretty good. So the first conservation law for Newtonian point mechanics is the law of conservation of energy. That's just one equation, because it's a scalar, for however many degrees of freedom that we have here. In this case, point particles in space 3 times n degrees of freedom. Okay, we have to get rid of this. I'll refer to it. It's in your notes anyway. Okay, so another conservation law. Here's what we're going to do. I've just erased my collection of equations. I'm going to have to rewrite them again. But I'm going to put a summation in front. So here's what we have. We have the sum of m sub I r sub I second derivative equals the sum of our external forces, I equals 1 to n, plus now we're going to have a double sum because remember we had Fij, those were the internal forces, here are the external forces. I've just taken that equation we had before, which was just Newton's second law for a point particle system, and I've added them all. So if one of them equals the other side, you know, if you have one equality, a sum of equalities is also an equality. Yeah, and I not equal to j. So what can we do here? Now we're going to invoke Newton's third law, because for every pair of particles here, we have Fij is equal to minus Fji. And since we have this double sum, for every Ij, there's also a Ji in there. And of course, the I, with the subscript don't exist. So this fact here, these are vectors, implies that the double sum vanishes. And what that is, it's just the sum over all the internal forces. They all cancel out. Okay? Internal forces cancel out. That's something that we'll see more than once. And yeah, so we're left with this equation here. So we have, we can draw the following conclusion. Since this is a second time derivative, we can say that the first time derivative of this sum here, recognizably sum of linear momenta, so the total linear momentum. So the time derivative of the total linear momentum is equal to the net external force. The sum of all the external forces is the net external force. That's a single time derivative. And now we see if the net external force vanishes, then the linear momentum is conserved. Okay. So let's put that down here. If F net external equals 0, then capital P, this is where in your notes you have a lot more room than I do. But leave plenty of room in your notes. Space it out, fill in stuff, okay. Then capital P equals sum of lowercase p sub I, sum of m sub I r sub I dot is constant. So that's the conservation of linear momentum. Okay. The conservation of the total linear momentum. So write down conservation of energy on the original one here and conservation of linear momentum. So far I'll just write we have conservation of energy, and we get that when f sub I is equal to minus gradient u, so we have such a function, and conservation of linear momentum, comma, when f net external equals 0. So you see we have the conditions on these conservation laws. Okay, I'm going to look at our timing here. Okay, very nice. We don't want to go too long today, the first lecture. These lectures are all one take, no edit. Okay. So that's why we can do them and post them fairly efficiently. One take, no edit. Okay, so we have those two conservation laws. There's a really nice theorem that goes with this. I'm going to showcase this expression here. Okay. Can we send that up a little higher? Yeah, good enough. Okay. See, I'm going to rewrite that equation, and we get a really nice corollary out of it. The idea with these point systems is that the whole world is made up of atoms, made up of tiny constituents, and we're trying to reproduce everything visible just in terms of atomism and the laws of mechanics. Well, that only goes so far, obviously. There are field theories to come later, but this is the attempt to explain everything in terms of point mechanics. So let's go ahead and repeat this equation here. We have the time derivative of this expression here. The net external force on our system. Remember, we're now talking about that point system, the cloud of little particles that interact with each other. And there's something else we can do here. I think what the quickest way to it is to define R as being equal to sum of m sub I r sub I, sum of m sub I. Yeah, what is that? Of course, everybody recognizes that's the definition of the center of mass of our point system. It has a center of mass, that's its definition. So, yeah, let's go ahead and write it down. That is the famous center of mass. And what we can then do is just multiply this over your sum of m sub I and take two derivatives, or second derivative. Okay, so I cross multiply, take two derivatives, or take two derivatives, then cross multiply this total mass, after all it's just a scalar, equals sum of m sub I or sub I, second derivative. But what is this? Well, this is this thing here, second derivative if you want it. So that is equal to f net external. And if I want to, I can just say the total mass times the acceleration of the center of mass is equal to the net external force. Here, put a box around this. Yeah, that's Newton's law for a point system. It looks just like Newton's law for a point particle. And therefore you can say for this extended system of point particles, whatever they're doing, it moves, or the center of mass of that system moves as though the net external force were acting at that center of mass. Okay. This looks just like the Newton's law for a single point particle that we started with. It's for a system of particles. Yeah, but what is a system of particles? You know, you could have a tennis ball. That's certainly a system of particles under the atomic point of view. And of course, we just treat this thing. You throw it, it does a parabolic trajectory. And its center of mass is doing a parabolic trajectory. So of course we've always used this expression because we don't actually have point particles in day-to-day life. We have extended objects. But you could have an extended object. You know, let's call these our examples. This is the example of the baseball being thrown. Okay. Another example, though, is of a horseshoe being thrown. Not a Greek letter. This is an actual horseshoe. And where's the center of mass of that horseshoe? Center of mass is somewhere here. You launch that horseshoe and it's going to tumble and do what it does, but its center of mass will be describing a parabolic arc. Good, so point mechanics gives us back our basics. Okay. Yeah, so far we've done some point mechanics review. And I've done some calculations, and if you space your notes wide enough and you can fill in, so you can do these notes, you can fill in any missing steps that you don't quite understand, if that's the case, and you should have something logical. Your notes will look more logical than these boards here, if you leave enough space between everything. Good. Let's see, you know, there is one more conservation law. I think I'll do that. Let's see how we're doing for time. Well, no, I'm going to save it. This is the first lecture. We're going easy. In fact, you know, this is a 4-unit class, so we could have really long lectures. What I had been doing when we're all meeting together is I had been doing an hour lecture, and then we were taking a break, and then people were coming in and working problems at the board. And I really regret that we're not getting that practice this semester, because it's really the greatest thing. So we'll see how the whole thing develops. I'll post at least 2 lectures. They'll tend to be a little longer than this one, but as far as, you know, who knows, middle of the semester, if something changes, I was trying to get us to get some permission for face-to-face face-to-face meetings, but that didn't work. Nonetheless, there are no wasted semesters here in physics. You know, we're just gonna be here doing our thing, okay, doing our calculations, and we'll see what comes of it, okay. So once again, I'll stop it here. Next time we will do the angular momentum, which is an interesting calculation along these lines as well. That's the first thing I want to say. You now have something to turn into me on Friday. I didn't assign any problems per se, but you've got these notes you want to turn in and fill in any missing points. That's the second thing. Email me at my email. I haven't set up any Canvas stuff yet, which I'll do later. So at my email account, as I said at the beginning of the hour, make sure you put your name in the subject, your name in the class, and then it'll be easy for me to find. Okay, I'm just going to wish you a successful semester. Hope everybody enjoys it, and we'll see you later.